First of all, thank you very much for the stipend. So I worked at LTU on my licentiate on particle generation for geometallurgical process modeling. In practice, geometallurgy is located at the boundary between geology and process mineralogy. So we're trying to integrate these two processes into a predictive model. So we'd like to be able to predict, even before a block is mined, what sort of recovery, what sort of grade in the mineral of interest we'll obtain after the processing chain. In particular, I've been working with the process model, that is the flow sheet of the concentration plant. So the scope of the work was to see whether or not we could generate the right particles to use in process model simulation. So if we have a good simulation of the process model, we need to have representative particles of our real ore. And to do that, we need to have a look at texture, we need to have a look at mineralogy, chemistry, and take all that into account. So we see already from the beginning that there were several levels of details. The first one was the chemistry, so chemical elements. The second one is minerals. It's already more complex. It has an idea of geometry inside it. And the third one is our particles. These are the basis of mineral processing simulation. So we're interested to see if we could get better prediction by working with particles. So small object that contains several mineral phases, and see if that extra information would give better result compared to working with elements. So it was done in several phases. One was to look at how to characterize the minerals. So what sort of data do we need? What sort of input? And then moving towards process simulation, look at what sort of unit processes we would need, what mathematical models we need to use. So the first step and the second step was to first acquire the data properly. Then secondly, I tried to link, let's say, the raw data with minerals. It seems like an innocent step, but it's already building a model of reality. So the step is not so innocent as it looks. So in here, for example, we have a copper ore containing as ore mineral mostly chalcopyrite in red. So this one is an example of segmentation based on normal camera image. That is no expensive sensor, very basic, very cheap, and very quick sensor. So just essentially a normal camera. High resolution, but still quite cheap. And do color-based segmentation based on some machine learning techniques. And that's already a first way to do that. I mean, we can use, depending on the scale, microscopy. We could use, in the future, X-ray tomography to get 3D information. But otherwise, even color information can be enough in some cases. So once we had a model of this mineral phases, the second step would be to convert that into particles to use in simulation. So to do that, I propagated cracks in this assemblage of different minerals. So here the scale has changed a little bit. In red, what you see in red, maybe it's a bit too small, but it's 150 microns. So we changed scale from drill cores, so a couple of meters, centimeter scales, down to microns. By propagating fractures, we started to generate particles. It's like a virtual rock breakage engine. So we generate hundreds and thousands of particles, and then we can use that as a feed for a simulation. So all the different steps were first to analyze the rock texture, try to see if we can convert an image into numbers, meaningful numbers, if possible. Then classify the different textures. Geologists know to do that very well because they're experts, but most of the time machines are having a hard time at discriminating between different ore types. So I developed some indicators to do that. Then how to break the texture into different particles and make sure that the results are in line with what we observe in the process. and then use this particle in a flowsheet simulation. So for that, we need to have the right software, the right data flow, and also we need mathematical models that operate at the particle level instead of chemical level or even bulk mineral, that is unsized minerals. And the last step would be to generate predictions and validate them. And that's currently still going on. Reported partially the results in the licentiate. So the conclusions I drew from the licentiate was that predictive models are useful for geometallurgy. This wasn't obvious neither, because of the cost that it involves. I mean, it's a lot of work and resources to put in. Then rock textures could be quantified at different scales. So instead of having to describe a rock textures in terms of veining, disseminated, or adjective that can vary from a person to another, we can actually derive a vector or matrix that allows us to, for example, talk about the distance between two textures, two rock textures, and in turn talk about the different degree of liberation after comminution for different rocks. So that was an interesting part. And then if we measure these textures and quantify them somehow, we can generate realistically particles for flowsheet simulation at the right level. And that was done through mostly data management and done in collaboration with Autotech mostly. So in terms of the perspectives, one thing was starting to talk about digitalization because, well, this is a very broad definition, creating value based on digital technology, of course. But in this case, we actually use mathematical models to have a look at something that has an impact directly on the plant. So measure or predict something that we couldn't before, based on mathematical models running on computers. So that's an interesting aspect of the work. Secondly, machine learning was used very much in this work, mostly for image processing, but also for analyzing and verifying the results. This is still going on. We're now working with different technologies around convolutional neural networks, moving towards deeper networks and, let's say, real-life, industry-ready technologies. And the last idea was, okay, now we have models. We might have good numerical models, but not all of them are good, and not all of them are useful. So in the future, I think I'll try to focus on developing tools to quantify the real value created by numerical models. It's one thing to have a tool, then it's another one to have a good tool, and a tool that can be assessed. And that's a major issue. I mean, we need to be very careful about what we do and see if it actually creates value and not just entropy. Well, thank you very much. I'd like to thank also the main partner of the study in PrEP. So here they are. Thank you very much.